Hi scholars, I hope you're all doing well. Today we are going to continue our analysis of series and parallel circuits, and we are going to be doing that by diving a little deeper into the relationship between the current, the voltage, and the resistance within a circuit. So for the last 4 days, we've been doing an argument-driven inquiry, and we were exploring how these four quantities or three quantities are related to each other. So today we are going to dive a little deeper into that by doing a reading to see what the consensus of other scientists is about the relationship between these quantities that we're looking at. And we're also going to do some practice problems in order to analyze a model of a circuit in order to determine what the total and equivalent resistance is within the circuit. Again, that's being able to figure out what the total resistance within a circuit is going to help us better understand the relationship between the resistance, the voltage, and the current. So that means that Ohm's law is making a comeback. We're going to be using Ohm's law again today and tomorrow to look at some problems. All right, so the way we're going to do that is, like I mentioned, first we're going to do a reading, then we're going to go over some key points, check for understandings, and then at the end you're going to have some time to do some practice problems. Okay, so we don't have a do now today. We're just going to dive straight into the reading so that we have plenty of time to model some problems and to go do some check for understanding before you do your independent practice. So take the next 10 minutes to read and take notes in your notebook. Right. The reading is a PDF file. Well, sorry, it's not a PDF. So the reading is an image. So you're not going to be able to highlight in your classwork document, but it's imperative that you take notes in your notebook. And particularly pay close attention to the relationships between voltage, current, and resistance for the series and the parallel circuits separately. Okay. So again, take the next 10 minutes, and when you're ready, you can press the video, plus play again so we can continue on. Right? Happy reading. All right, let us move on. So let's do a quick review of the key equations in the series circuit. You should have these in your notebook already, but if you don't, please make a note of them now because we are going to be using them. Right? So this is the same circuit, the same series circuit that is in your reading. And the key equations that you should have are these three here. So again, this is Ohm's law. I mentioned that it's coming as a comeback, so we're going to be using this throughout the lesson. And for a series circuit, the voltage is the total voltage in our circuit, so the total voltage of the battery is going to equal to the voltage that drops through each one of these resistors. Right? I'm going to explain what that means a little bit more detail in a second, but you should have this equation from your notes. And then we also saw in our inquiry, in our ADI, that the current everywhere in a series circuit is the same. So it doesn't matter where you are in your series circuit, the total current equals the total current that goes through this first resistor, equals the total current that goes through the second resistor, and then it will equal the total current that goes through the third resistor. And then this is important, and then this is new, that the total resistance of a circuit in a series circuit is equal to the sum of the resistors. So in this case here, if I would add, to find what the total resistance is, I would just add R1 plus R2 plus R3. Right? All right, so let's do a quick check for understanding and see, take the next minute to find what the total resistance of the circuit is. Right, so given these three resistors, what is my total resistance? Press pause. Okay, so let's check to see what we did. So based on the equation that I had on the previous slide, it said that my total resistance is equal to the resistance for my first resistor plus the second one plus the third resistor. Right, so I see here that there's 3 resistors. I'm going to label these so that it's easier for me to remember which one's which. So I just did. And now I am going to just use my equation here to add them. I mean, you can add these in your head, but this is just practice for us. Remember, this is 20 ohms plus 30 ohms plus 50 ohms. And then, so now my total resistance is going to be 50 plus 50 is 100 ohms. So this is the total resistance here. So now, just as a separate question, how could I find the current that's going through this whole circuit? And so just think for yourself, how could we do this? You're right, we should be using Ohm's law, right? So remember, Ohm's law is voltage is equal to the current times the resistance in the circuit. So here, now we're specifying that these are the total values within the circuit, the total resistance, the total current, and the total voltage. So here, I look at my battery, the total voltage is labeled next to it. And then I just found what my total resistance is over here, so I'll be able to find what all of the current is in the circuit. So let's solve for current. So my voltage, again, is going to be equal to my current times my resistance, but since I'm trying to find current, I'm going to divide both sides by R. So then voltage divided by resistance will equal to my current, my total current. And now I can just plug in numbers. So 125 volts divided by my total resistance, which is 100 ohms, will equal my total current. And then these two numbers will just give that 1.25. Remember, the unit for current is amps, will equal the total current that's flowing through this circuit. So here, throughout, my current will equal 1.25 amps. Okay, so you should have, please write everything that I just drew in your notes so that you can use this as a model, because you're going to be solving problems like this on your own at the end of this class. Right, so if you weren't following along in your notes, press pause now to make sure that you write this down. Okay, great. So now that you have this all in your notebook, let's move on. So let's go over the, the key equations for parallel circuits. So again, Ohm's law is here as a reminder that that's the relationship that connects all of these together. So in your ADI, you should have noticed that in a parallel circuit, the voltage from the battery is equal to the voltage that was going across each one of the light bulbs. Right? So here we see that the voltage is equal across each one of the circuit components. And then we also noticed that the current actually divides. So we saw that there was a certain amount of current that was coming through the battery, and once it reached this point, this junction, the current actually split. So some of the current went through bulb 1, and then some of the other current went through the second bulb, right? And then this here would have been my total current. So, and then afterwards, at this junction here, all the currents added up again, and then the total current is what flowed back into the battery at the end. Okay, so you add all the individual currents that flow through each resistor to give you what the total current is. To figure out what the total or equivalent resistance is in a parallel circuit is a little bit more complicated than the series one. So here we see this weird equation where the inverse of the total resistance is equal to the sum of the inverse of each resistor. So it's a strange relationship. All you need to know, you just need to know this equation and how to use it to find the total resistance. And we're going to practice that now. Okay, so a key point before we practice the total resistance, finding the equivalent resistance in a parallel circuit, is that when you have, so we talked about before that the more resistors you add into the circuit, the more resistance the circuit has. So that only ends up being true for a series circuit. because for a parallel circuit, it turns out that the more, when you add resistors in parallel, it actually decreases the total amount of resistance in a circuit. So here we have two 4-ohm resistors that are connected in parallel. So if you were to add these together, and it turns out to be a 2-ohm resistor. And if you have two 6-ohm resistors in parallel, it actually ends up adding into a 3-ohm resistor. And I mean, you might be wondering, like, why wouldn't you just put a 2-ohm resistor there instead? Like, what's the point of connecting things in parallel? And actually, it's important to remember that resistors aren't there just to decrease the current in a circuit. They have functions. So we've looked at light bulbs as a resistor. So a light bulb has a function of having light. Like a speaker could be connected into a circuit also, and it also functions as a resistor because energy is lost when it goes through the speaker. And then, of course, the function would be to convert electricity into sound, which is a thing. I had mentioned several lessons ago that our house circuits are connected in parallel as well. So it makes sense that the more things you have plugged into the walls, it kind of decreases the amount of energy that's lost in the house. So you wouldn't want to have your appliances collected in series. You would want to have them connected in parallel. So there's a lot of really important consequences that come out of this concept that might seem a little strange. Okay, so now let's put this into practice. So let's find the total resistance of the circuit. So the first thing I want to do here actually is going to label my resistors. So this is going to be resistor 1, this guy will be resistor 2, and this will be resistor 3. Okay, so I'm going to start over here. Our equation to find the total equivalent resistance is 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so now that we've identified which resistor is what, let's plug that into our equation. So we have 1 over RT is equal to 1 over 20 ohms plus 1 over 100, sorry, 1 over 100 ohms plus 1 over 50 ohms. You're going to need a calculator to do this. Otherwise, it's like a pain to just do each one individually and then add them up together. So if you plug these three numbers into a calculator, you get 0.08 ohms, right? So that's equal to 1 over the total resistance. So here we're not fully finished because the variable that we're looking for is actually in the denominator on the other side. So here we're going to have to cross multiply these two numbers in order to figure out what our total resistance is. So I'm going to come over here. If we do that, I bring my resistance to the numerator on the other side, and then this number to my denominator on the other side, and I end up with 1 over 0.08 ohms is equal to my total resistance. And then now if I again plug this number into a calculator, then I find that my total resistance is actually equal to 12.5 ohms. So here I see 12.5 ohms is significantly less than any of the resistors that are here connected. Right? So again, to the point that the more resistors you add in parallel, the less your total resistance becomes. Okay, so then now, what if I ask, just like we did in the other question, what's the total current that's flowing through this circuit? So I can find that by again using Ohm's law. So Ohm's law is V equals IR. And I'm going to use this. Again, if you haven't been writing this down in your notes, please do that now, because you're going to need to know how to do this for the independent practice problems that are coming up. And this can get complicated, so it's really important that you have a model in your notes that you can refer back to. Okay, so now let's find the current. So we said that our voltage here is labeled right next to my battery, so that's 125 volts. And then I'm going to divide it by my resistance so that I can find out what my total current is. So I'm dividing this by the total resistance. We'll label this T. RT, so we said that's 12.5 ohms, and that's equal to the total current. All right, so then I divide these two, and this is 10 amps. So 10 amps is the total current that's coming out of this battery here. All right, so it's the total current. But we had said previously that in a parallel circuit, the current actually divides up. So at each one of these junctions, the current is going to split. So there'll be some amount of current going through here, and then this is going to continue, and then over here, the current will split again. So there'll be a certain amount of current 2 going through here, and then over here, there'll be some current I3 that's going to go through each one of these resistors. So how could you find the current that's going through each one of these? What do you think? Yes, we're going to use Ohm's law again. So I'm not going to show how to do all three, but up here at the top, I'm just going to show for this first resistor, if I want to know what the voltage, we talked about how the voltage in a parallel circuit is the same in every one of these. So the voltage across each resistor is going to be 125 volts. And then I know what my resistance is right here, so then I can find my current. And so let's do that. Current is through the 1 and my resistor 1, so it's 125 volts divided by 20 ohms. That will be equal to my current. So then if you divide 125 by 20, you should get 62.5. No, sorry, it's 6.25. Reset. Oops. Amps is equal to my total current. I'm sorry, not my total current, just the current going through this resistor here. Okay, and then you can repeat the same process for R2 and R3. In your classwork document, if you haven't noticed yet, I'm going to show you. You have, so below the reading that you just did are these tables. Right, so I went in ahead and filled out what the values for the resistors were. So then you can add what the total resistance is, what the voltage is across each one of these, and then what the current is as well. And then the way that you're going to answer that is using the equations that you wrote down. And I am also going to add another table here that you can use that will show you what the relationship between all of the equations are. Okay. So make sure you have your two tables complete, and then come back when you're done. All right, moving along. So just want to discuss this idea of resistance one more time. So there's this thing called the toll booth analogy that can help us understand a little bit better the relationship between current voltage and, between current voltage and resistance. So this first image here it kind of compares resistance to toll booths. Okay, so if there's only one resistor or one toll booth, then the cars, which are analogous to the charge that's flowing through, that's coming out of the battery, the charge can only go through one particular resistor. So it can only go through one toll booth. So the cars are going to slow down, but there's only one obstacle, and then afterwards they're able to continue and speed away quickly. If you have three resistors that are placed in series, it would be the equivalent of having three toll booths back to back. So that really stops the flow of current. it prevents the charges from flowing as freely as they should be. And then, so that's why it slows it slows down the current, well, the amount of current that's flowing. And then for a parallel circuit, the analogy here is that you have 3 toll booths side to side. So even though there is still an obstacle there, there's more options for one car to go through. So let's say this light blue truck, as it was coming in, it was like, oh, there's 3 paths I can take. So then it goes through one, which allows this red car to go through the middle one, which allows the blue car to go from the other. So that means that when charges reach a junction, then they're like, oh, there's several places where I can go to. So then they move, creating space for other charges to move quickly and simultaneously as well. So it kind of, having resistors in parallel, like widens the highway, so to speak, so that it permits more charge to flow at the same time. Okay, so hopefully this analogy kind of helps understand a little bit better the relationship here between resistance and current. I understand that it can be a little confusing, so I just wanted to make sure I could explain it in another way. Another way that I wanted to relate these quantities is discussing a little bit more about potential difference. So potential difference, I made an analogy a while ago how like potential difference was like going on an escalator. So here I just want to give you another visual representation of that. So here it compares our circuit, the circuit with 3 light bulbs, to basically just like steps. So the potential that's provided from the battery kind of raises the charge all the way up to this top part here. Okay, so then from as my charge is going from point A to point B, like it's basically just going in a straight line. It's not really losing any energy. I mean, there's a tiny, tiny little bit of energy loss when current flows through a wire, but it's not significant. But then when the current goes through a light bulb, it loses a big chunk of energy because of that energy is being transformed into light, and like we actually get to see it. So energy is lost, so it's like going down a step, right? So it's lost a step of energy. And then it's flowing through the wire, barely energy gets lost, but then when it goes to the next bulb, again, another big jump happens, right? So there's a big chunk of energy that's lost again. So, and then my current continues, the charges keep going, and it goes to the next battery, and bloom, lose a whole bunch of energy again. And then now I'm back on the ground. I'm at ground level. My charges don't have any energy left. So then they make it back to the battery, and then the potential voltage, the potential gives it like the energy back for the electrons to continue flowing, right? So these jumps here down are called, they're called voltage drops. Right? And we discussed this term in the last ADI lesson. All right, so voltage drop is the energy that's lost every time the current goes through a light bulb or any type of resistor for that matter. Okay, moving along. So the relationship between resistors and potential difference in a parallel circuit is a little bit different. So here, when the current comes out, the current comes out of a battery, it flows, and then it reaches this junction here, it reaches a point. And you guys, like we noticed in the ADI, that the voltage across each one of the resistors was equal to the total voltage. So say this was 5 volts, right? The voltage across this one resistor was 5 volts, the one across the second resistor was 5 volts, and so was through the third resistor. The reason why that is because if you have, in the same way, comparing this to the toll booth analogy, you have a charge that's coming through here, and then it gets to this point, and then the charge is like, oh, I can go through resistor 1 or 2 or 3. It's like, I'm going to go through resistor 1. So that one charge experiences only one voltage drop. Right? So there's just one drop of one loss of energy from that one charge. But then another charge comes through this second resistor, and then it only experiences one drop. And then another charge goes through this resistor here, and then that one will only experience that one loss voltage drop through that one resistor. And then all of the different charges that went through the different resistors are going to end up down here at the bottom level with no energy left, right? And then the battery will continue the cycle. So that's kind of what this diagram is saying here as well. And so if you want to take notes on that on your notes, you can pause now and do that. All right, so moving along. So a few key points. There are different mathematical relationships that can be used to compare the voltage across the current, the voltage across and the current through individual components of a circuit. Depending on what the components are, either if it's a series or a parallel circuit, right? So that's everything that we just talked about. And then to find the overall current through a circuit, it is necessary to find the equivalent resistance of the circuit. And then the equivalent resistance, again, this vocabulary word means it's just equal to the total resistance in the circuit. Right? So we did this already in the two problems that I modeled. First, we found what the total resistance of the circuit was. And then once we found the total resistance, then we were able to find what the total current was. All right, this diagram here is in your classwork document also, so you can refer to this if you need to. This summarizes everything that we just talked about, okay? So refer to that for the independent practice problems that we're about to do. So for the remaining time in class, complete problems 1 and 2 in the independent section of your classwork document. You can refer to the models that we just did to help you successfully solve these problems, right? There's no exit ticket today, just complete these two problems, and that was all for today. So I hope you have a fantastic afternoon and have a great day. Goodbye, y'all.